So, if both f and f inverse are differentiable, how would you describe it to a CalcBC kid or remind them of what it means? Okay, but aren't most functions able to be differentiated? All functions can be differentiated, so hold on, wait a minute. When is a function not differentiable? At a point where the derivative, does not exist, right? Differentiable. F and F inverse are differentiable, able to be derived, all the derivatives existing, all the derivatives for all real numbers. And, this is where we got stuck last year, and if F inverse of A equals B, what's another way of writing that? Because the AP can give it to you two different ways. Either F inverse of A equals B, or F of B equals A. Right? They can give us an inverse point, an inverse clue, or they can give us an original point, an original clue. They can give it to us in a table, they can give it to us in a graph, they can give it to us as a point. But if we're trying to find F inverse prime of A, we have to take the reciprocal. We have to take the reciprocal of the slope at the corresponding point of the original function. So, how would you do this example? Using that forever card from last year. Ready, set, go. You tell me. I'm going to zoom in on this because we don't technically need the triangles yet. How would we solve that example? Fine. F inverse prime of negative 1/2 for f of x equals sine of x. You could. I think that's dangerous. But you could. You will eventually. John's totally right. We will have to plug in negative 1/2 to that equation somehow, somewhere. But where? What's the notation for the derivative first? And who's B? You guys agree? Or wouldn't B also be? Remember how this was tricky? Negative 1/2 is an x of the inverse. If it's an x of an inverse, who is he of the original? The y. Negative 1/2, it's the x of the inverse, it's the y of the original. So John, let's go back to what you said. If I was to plug in negative 1/2 correctly, where would I plug it into? Yeah. I would need to set my entire function equal to negative 1/2. So sine of b, if you want to think about it that way, sine of b is equal to negative 1/2. There's a lot going on, and this is something that you guys get confused quite easily in general. The derivative of the inverse at negative 1/2 is 1 over f prime of not negative 1/2 of b. Who is b? Well, if I'm given f, b is what f of b equals. So sine of b is equal to negative 1/2. It's the y value of the original, or the x value of the inverse. So, Lorenzo, what are you saying? But why? He's up here, I think, and he's saying, okay, when does sine equal negative 1/2? Well, here's the problem. In order to find that, Lorenzo went all the way around the unit circle to the 3rd and 4th quadrants. 7 pi over 6 and 11 pi over 6. Here's the problem though. If we were to use the inverse sine function where there's only one answer and one answer only, both of his are wrong. Because it'd be negative pi over 6, because sine inverse only goes between negative pi over 2 to pi. So getting to his same location of 11 pi over 6, but getting there in a negative angle sort of way, I could technically say, oh, I'm doing f prime of negative pi over 6. Negative pi over 6 is my b. Now here's the dilemma though. What's supposed to be outside b, or what is b supposed to be inside? The derivative of f. Who is the derivative of f? So I take the derivative of sine, I get cosine, but the person I'm plugging into cosine is not negative 1/2. I'm considering for what x value will sine be negative 1/2. If we use the inverse sine function, now usually guys with trig, they would give you some sort of like interval, and so then, Lorenzo, maybe yours was more right than mine, but they only have you choosing one answer. Does that make sense? So I'm assuming sine inverse. Since I didn't put any interval, I'm assuming sine inverse would give you a positive cosine, which would be different than the third quadrant. So then my cosine at negative pi over 6 is what value? Rad 3 over 2. So does it make sense that we would have 2 over rad 3 as our final answer? Not in the fourth quadrant. Not in the fourth quadrant. Now, if their angles got us in the third quadrant, if they gave us angles, then yeah. Well, then yeah, but in this one, no. In this one, no. Now, this is all well and good. It is tricky, and we'll deal with the trickiness when it comes, for the most part, okay? But what is actually the title of section 4.3? Yeah, I just put inverses back there because we're going to review inverses, but the actual point of the section was trig. So, there's another way to think through trig. And the other way of thinking through trig is actually going to open up, to some degree, I'm just introducing it, but open up a whole new type of integration. Now, sadly, it's a whole new type of integration that our AP doesn't test, but any calculus professor would expect you to know and do in Calc level 2 and 3, called trig sub. Integration by trig sub. Now, guys, we haven't even done integration yet, although there was that homework, wasn't there? That introduced the idea of an antiderivative, something about derivatives backwards. Wasn't there a homework? Patricia, you were talking about that one. There was a homework that introduced it just a little bit. But we're not introducing, or we're not doing integration today, but what we're seeing today forms the foundation to this thing called integration by trig substitution. So I'm going to show you how inverses work with triangles. I think I did it a little bit last year. But I'm doing it again this year because we're going to use it again at the end of second semester to do a trig sub module that is not for the AP, but any college professor would expect you to be able to do. And some intervals can only be solved using not this differentiation technique, but it's so similar and so related. So what's going on? We are going to figure out derivatives of inverses one more time. Yes, I know they're formulas you can memorize. But some of you aren't so good at memorizing them because I graded all your forever quizzes and finals last year. Some of you are fine. We're fine. Could be fine again. Studied them again. However, where do they come from? Where do they come from? Guys, is there another way to write an inverse besides y equals sine inverse of x? Yes, we could also do arcsine, but is there a way of stating the inverse relation without using a -1 or an arc at all? Can't that be an inverse trig also? How to switch when the x's and y's have been switched? Right? That's also inverse. So here's the dealio. We're coming off of the implicit differentiation section, true? Fussy. And coming off of the implicit differentiation section, we're like, oh, you don't need to fussy. You get y by itself. You could have just derived it like that. And the answer is most definitely you could have. And if we derived it like that, we would have done d dx to the whole side. So instead of taking the derivative needing a formula for arcsine or sine inverse, we could have just taken the derivative of a sine. How easy is that? What happens when we take the derivative of, well, first of all, x 1 equals the derivative of sine. So dy dx aka the derivative of this original inverse relation, which is technically the same thing as this dude, is equal to 1 over cosine of y. Exactly. Done. Well, is that your forever code? The derivative of inverse sine is 1 over cosine of y? No. What does it look like? U's, and all the u's are in terms of what? X. Oh. So guess what? This is the exact same thing as that, except this one's in terms of y, and that one's in terms of x. The whole 1 over the square root of 1 minus x squared, or u squared times u prime. But yeah, 1 over the square root of 1 minus x squared is that, but how? This. Anytime you have a sign, aren't you given an opposite over a hypotenuse? This is the part that's important here. Any sign is an opposite over a hypotenuse, true? Oh wait, but it's not a fraction. Oh, it's okay. I'll make it one. Anything inside a sign is an angle. True? So if I were to label a triangle, wouldn't that be y, and wouldn't that be x, and wouldn't that be 1? Think about it. So Katoa, any sign of y is an angle, opposite over hypotenuse, my x over 1. What am I missing from my triangle? Wait, why does it even matter? Well, who do I want again? Cosine of y. Doesn't cosine need adjacent over hypotenuse? Oh, I need adjacent. Well, how do I solve any right triangle? C squared minus b squared is a squared, right? So couldn't I make this the square root of 1 minus x squared? So where does the formula come from? Is it clicking any better than it did last year when I showed it to you? This is just plugging into a triangle, the pieces, taking the derivative of the inverse relation, and then being like, oh, hey, look, adjacent over hypotenuse is just the square root of 1 minus x squared. So guess what the derivative of the inverse function is? If it's a u times u prime. Remember this year how I talked about how some of you would mess up last year? The derivative of tangent, the derivative of secant, the derivative of cosecant, the derivative of cotangent, and I said there should be no excuse because you could always use quotient rule to sines and cosines, right? Guess what you would also miss? Derivatives of sine inverse, cosine inverse, tangent inverse, secant inverse, cosecant inverse. You know what the ironic thing is? You can always find it from triangles. Now, it gets harder depending on which one we're doing. And it might be weird, once again, that I'm taking all this time when it's like just memorize. But remember, there's something coming, and that something coming needs you to think about this idea of plugging into a triangle and getting out from a triangle. Variables and solving for sides and all that sort of stuff. It's more complicated, it's used in integration, and it makes some impossible things possible. But right now, we're just seeing where the rules come from. What would have changed if we had cosine? What would have changed if we had cosine? If we had cosine up here, what would the derivative have been when we went to do the implicit? Negative sign. Negative sign, hold on, x over 1 would have been adjacent over hypotenuse, so the square rooty guy would have been the opposite, but that's okay, we would have needed the opposite for the sign, so it would have been 1 over the exact same thing, but with a, derivative of cosine is negative, but with a negative. They're the same thing, just cosine is a negative, because the derivative of cosine is negative sign. Oh, that's why it is. Okay, so that's sine and cosine, but what other inverses do we have? Let's see what I have ready. Oh, that's no fun. We just did that. Forget that. Ah, what if we have tangent? Inverse. Ooh, of 2x. Oh, sure. Of 2x. What if we have tangent inverse of 2x? Guys, how would you state the inverse relation on this one? What do we do with the 2, right? It's like, okay, do we just put an x and put a y with a tangent? Okay. You don't have to guess, because what I did on the last page, it looked easy, but to be honest, there was some math involved. Do you know how I got this? Why don't you just take tangent of both sides? What happens when you take tangent of tangent inverse? X So what's the inverse relation? 2x equals tangent of y. Do you see how it's a little bit different than what we just saw on the page before? You would have taken sine of both sides and you would have gotten x is equal to sine of y. So there actually is some math involved as to the inverse relation. You're getting rid of this inverse notation and saying, whatever, I don't need the y by itself. I like tangent better than tangent inverse. So you just take tangent of both sides and say, okay, whew, there we go. All right, derive implicitly. Wait, pause, man. You guys finish it and show me why the rule is what it is. Go. I'll start playing here. You guys finish it. Try to follow the same technique. Can you show why the derivative of tangent inverse is 1 over 1 squared plus 2x squared all times u prime? Careful. 2x quantity squared times u prime. I don't want to multiply. Feel free to collaborate in groups if you get stuck. I don't mind. All right, how'd it go? Did you guys get a u prime also? You were supposed to. Just naturally, though. You didn't have to remember it. It just kind of happened. Well, it sort of should happen. Hey, if I divide by secant, is that the same thing as multiplying by cosine? Isn't 2 over secant squared? Yeah. Oh, that makes life a lot easier. I'm just looking for, well, hold on. I need to find cosine to square it, right? I need to find cosine to square it. Why? Because the derivative of tangent is secant squared, and when I divide, okay, it becomes cosine squared. So when I go to fill into my triangle, did you guys see that this could be over 1, tangent is Opposite over adjacent. Did you? Or adjacent, yeah. Like adjective, isn't it? Y. 2x. 1. Wait. Adjacent, not hypotenuse, right? Oh, how do I solve? A squared plus b squared is c squared. So it's the square root of 1 plus 4x squared. True?
It is square root.
And when I go to plug in cosine, which is adjacent over hypotenuse, don't I get to plug in 1 over the square root of 1 plus 4x squared? And if I square that, 1 squared is just 1. Square root squared just cancels out. And don't I end up with 2 over 1 plus 4x squared? And that is the derivative of tangent of 2x. The cool thing is chain rule just kind of happens. Because this would be the same thing as if we had started at the very, very beginning, u prime all over 1 plus u squared. Oh, tangent of 2x. I ran out of space. Tangent inverse of 2x. I apologize. The original dude that we were trying to derive. Can we keep going with cosecant and secant? Yes. And if it wasn't a minimum day, would we? Yeah, probably. But does it at least kind of make sense? I'm saying, okay, what if you didn't know the inverse? Okay, fine. Use your math to state it implicitly without the inverse. Take the derivative, but to take the derivative, you're in terms of y. You can't stay in terms of y. So to get out of in terms of y, come back to your original expression, which we've had to do a lot with implicit, right? Analyze what's been given to you. Okay, maybe needing to go to a triangle and solve a triangle. Then plug in for the trig and magic. It's not magic, it's math. Okay. So, are there rules? Long story short, yes. Are there rules? Yes, there are rules. Could you memorize them? Yeah, probably should. Yeah, probably should. Kind of like the chain rule idea. Are there ways of breaking it down to maybe have a better conceptual understanding? Yes. But at the end of the day, do you need to be able to go somewhat quickly? Yes. So what would help you go quicker on the inverse trig? Knowing the rules. How many inverse trigs did they actually put on the AP? 1, maybe 2? I mean, they love to throw it on there just to see if you memorize it. But they could also throw on like a b to the u or a log base b of u. Who knows? You're going to throw on some weird derivative rule and just see if you knew it. Because they're nice. Some of you may be, whenever I put something like this on the board, kind of bored, annoyed. We have a forever card, whatever. But technically, is there research that shows that repeated writing does help things stick a little bit better in your brain? Yeah, that's a thing. So if worst comes to worst, just be like, well, maybe by writing it, I'll know it just a smidge better. Doesn't mean that's how you memorize. Doesn't mean that's how your brain works, but it is a thing. And it'll be in your notes. To keep on bringing your notes on. But some of you don't necessarily carry around your forever cards in your back pocket, but your notes you are kind of used to taking over. Go team. Long story short, could we make triangles for each and every one of these? Yeah. Even for the 2x one? Yeah. Yeah, we could. We can make triangles for all of them. But at the end of the day, if we have it memorized, can't we just kind of plug and check? We're the derivative of arc sine. Remember, arc is just like inverse in the sense of notation, for the AP at least. So if we were to take the derivative of arc sine, and if we know the derivative is 1 over the square root of 1 minus u squared times u prime, well, we didn't need a triangle to do that. If we had to. Or for arctangent, if we knew the formula was 1 over times u prime, well, u prime is 3, and then over 1 plus u squared, which is 1x squared. This one, u prime is a little bit nastier, so the simplification might be a little bit nastier. But once again, u prime times the square root of 1 minus, ooh, why is there just an x? Because the u was squared, and the square root squared just looks like, So can these kind of end up looking a little bit differently than you anticipate? Still an arc sine. cosecant of e to the 2x is going to end up being negative u prime, so negative 2 e to the 2x if we know our u prime, all over the absolute value of u times the square root of u squared minus 1. How do I square e to the 2x? Because e to the 2x, a power to a power, you multiply. It's okay, some of us are algebraic foundation is shakier than others, so sometimes some of you miss problems based on the little things. Exponent rules, power to a power, you multiply. So e to the 4x, 2x times 2 is 4x, minus 1. But wait a minute, why am I completely legally simplifying further? How was I able just to legally ignore that absolute value to reduce the top of the bottom? Who's your e to x graph? Is he always positive? Always above the axis? If he's always positive, what would his piecewise function look like? The same. It's the same thing. E to the 2x of absolute values. Remember, these can sometimes be redundant. He doesn't need absolute values. He will never go negative. His range is greater than 0, so therefore, well, forget that. That was redundant. That one will reduce with that one. Did I make a mistake? What's up? Oh, sorry. Joe first and then John.
Oh,
I didn't point out.
I just don't understand why is there a negative here.
Oh, did I do cosecant, subsecant? Sorry, cosecant, subsecant. I don't know why my brain's so, I don't know. Thanks, good. It's a positive function.
Would it be wrong if you didn't take out the conjecture?
No, just remember making a match. I want you to do that. So if this was the final answer, they would have another option with an absolute value with one little change. That you might be like, well, I know the absolute value can't go away. It must be this one. My math must be. You start second guessing and then choosing wrong. Okay, derivative rules for inverse trig. Is it a thing? Yes. Can you actually know where it comes from? Yes. But it'd be good to have it memorized. All right, section 4.3 homework is due tomorrow. You have like, you guys know what I mean. You got me how many years?
We could feed you.
Due on Monday. You're welcome. Due on Monday. I think I might be throwing something in AP Classroom. I was playing around with Mrs. Ranieri, like trying to help her out. It's not due on Monday. No problem. I am going to get you guys back in AP Classroom soon. But don't worry, if something notifies you, don't worry. Just homework for me.
What about it?
We talk very long.
You don't. Can't be good.
Like.
What's your other?
Every single program.
What's the standard temperature?
Yeah. You took chemistry. Okay, so I have a dilemma, and if you can help me, it'd be great. For the bonfire night, we're taking the white school ones, and so as for multiple student council kids, they carry 7 people, including the driver, and even then, with football guys, you should probably just have not. You're mad. Thank you. Do you keep erasing my files? I'm not keeping them. I was like, I need to schedule him then. I didn't know he was yours. I knew the bread was yours. And there wasn't room for the bread.